one of the mathematical examples, I should say, for this. But I'm going to just kind of run through the beginning slides because it was similar to what we saw in that intro document there. So we're going to look at what are called conditions to be met for a structure to even be classified as a truss. We're going to understand how the truss has two force members, how the structure utilizes trusses to support itself, and then what's called nodal analysis, the method of joints to calculate a force on each two force member. So let's jump into this first slide here. So first, the criteria for a structure to be considered a truss is that all members are linear, they're not curved, and they're joined at their ends. They're joined at their ends. So you'll notice that there's no connection to a middle of a beam. And what do I mean by that? Let me point it here. So this right here, from here to here, is one member. This is not one continuous length or member the entire way. So this is separate from this, which is separate from this. And at each of those locations, if we look at it carefully, we'll see that there's what looks like an overlap right here. So imagine these are like popsicle sticks when you think about these members, right? Each one of these members here is its own stick, and then they're connected here, 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 at all these different locations. Okay, let's go to the second criteria. The nodes themselves are idealized as pin connections, therefore transferring force between the members but not preventing moment. So when we think about moment, we're talking about things that rotate. So if you think about, like, if you had something on a swivel, right, and it had a pin going through it, and that object was able to like just swing back and forth like this, that's what we're talking about. It's not preventing rotation. It's a pin going through, so this thing can freely rotate about it. So the center line of the members, meaning the line that goes longitudinally through the member here, is where the actual pin connections occur, right at the center of each one of them. The third, well, let me show you actually with this image, because this is a great image of gusset plates. So this is what a gusset plate actually is on the left here. That's what it is, where you have a plate over it where there's reinforced bolts going through the actual members. But we idealize it as this. Okay, again, when a multipart member, we'll see that's what it actually is like. Why do you think we idealize it as this and do all of our analysis this way when in reality it's like this? What do you think the rationale is for doing all of your mathematical work looking like that, but in reality it's like that? Okay, good. Absolutely, Mort. It does simplify things a bit. Very good. So when we look at these problems, we're going to see that if we calculate that, as Brendan said, and we get like, oh, you know what, this bridge will sustain that amount of weight. And then suddenly one day, like, it snows for hours, right? And you have 10,000 more pounds applied to this bridge. Now you've got like a factor of safety there, good, a safe hold, just to make sure that it does actually perform up to standard. So again, idealize that way to make it simpler and so that we know that the actual thing is a bit stronger. The last criteria, or the third criteria, and the last one here, is that all of these external forces, they're carried specifically at the nodes or joints themselves. So we'll notice here, this is what we're actually looking at. This is not a truss structure, or this would not be considered to be a truss structure. Now, realistically, are things going to be carried only at the node? No, obviously not. And you think about an object going over a bridge, it's going to be applying forces throughout the whole member, and you're going to feel that, but the way we're going to analyze these is that there is a force that we can put as what's called a concentrated force at one of these nodes, when most things are actually distributed forces, right, over a certain amount of space. Any questions on the three criteria here? Okay. So let's take a look at what we're talking about with two force members. What do we mean by two force members? So the members that connect each of these nodes are either going to be in compression or they're going to be in tension. And if we look at the first one, we'll see that that's an example in tension. The second is compression. And let's zoom in on these to see this a bit better. So let's take a look at this one first here. So this example here is an example of something in tension. And let's think about that logically. This is the member itself right here. And tension is an example where you pull something apart, right? To create tension in a rope, you pull apart on it. So the applied force acting on this actual member at the end has to be directed away from the member. The same thing here. This force F is directed away from the member. But if we think back to physics from last year and you think about Newton's laws, every force has to be balanced, right? If we have equilibrium, if we're in a state of equilibrium, we know that we have a net force of 0. So as a result, if these members are feeling a pull outward due to the stress acting on them, then the nodes where the pins are located would feel a pull outward from it. And these two forces are balancing each other. These two forces are balancing each other. So when we look at tensile strength and we look at compressive strength, we can see if our member is in one or the other based on the direction of the force acting on the node. So we're going to do what's called a nodal analysis. So when the force acts away from the node, it means that the member is in tension, because then this force has to act away from the member to balance these two. So again, acting away from the node, we have an example with tension. And then if we go over here, we'll see the opposite. We'll see that if a member is in compression, it means that the forces acting on the member are literally pressing into it, these two forces here and here. Well, to balance this force, we have to have this one. And to balance this force, we have to have this one, noticing the opposite direction again. So if the force acts toward the node, as opposed to away from it now, in this case, acts toward the node, we're going to see that we have an example of a member that is in compression, not in tension there. So these are going to be the two things that we're going to look at. And what we're going to simplify things a little bit to say is like, hey, if we get a positive answer, it's one thing. If we get a negative answer, it's the other. Okay, a positive is one thing and a negative is the other. And what we're going to do to idealize everything is draw all of our forces acting away from the node. So if we get a positive answer, we know that it means that we drew it the right way. They're acting away from the node, it's in tension. But if we get a negative answer, it means that we drew our arrow the wrong way technically, and it would be a negative force on that node, which would equate to compression for that member. Let's see. This bottom one gives an example of both of these happening here. So if we take a look at this. So first, let's point out what's going on here. So there's an applied force on this entire structure, and it's right here, P. So there's some applied load at that location. This is the abutment on the right, this is the abutment on the left, and these two abutments are the reaction forces. Then, besides that, what they've done with this image, the illustrator here has separated all of these things, even though really this right here, this end of this member, lines up directly with that node. They're just putting a little gap there to show you what's happening. So if we look at this, here's what we're going to notice. We're going to notice that in this case, the force acting away from the node is to the right here, which means that this force must be acting back to the left to balance it. Newton's laws, again, equal and opposite forces. So this member here has a force pulling this way and a force pulling that way. So this member here is in tension, as is this member here in tension. Over here, we have a member in compression, we have a member in compression, and then finally the one in the middle, we have a member in tension. So that's the idea and the way we're going to classify these members. And why are we doing this? Why are we putting tension and compression? Again, because different materials have different compressive and tensile strengths. So while steel might have a very high tensile strength, it may not have a very high compressive strength. So we have to know whether it's compression or tension acting on the member to then see if it exceeds the limitations that are there for that material. Any questions on the concept of compression and tension here? Oops. Okay. All right. I think this is just an example, right, of a bunch of things that use trusses, and we already talked about this: bridges, buildings, domes, residences, towers, like cell phone towers and stuff. I'm going to skip right through that. We already spoke about that. All right. So let's take a look at this method we're going to use here. And we're going to step ourselves through it with this example, and then we'll look at an actual mathematical approach. So the method itself says the following. So we're going to use this method first to determine the force acting on any member, and that's the goal in this process. And if we look at the diagram on the right, we've got two applied loads, the 400 Newton load and the 800 Newton load. Then in the corners, what you're going to notice, and let's take a look at what's happening down here. In these corners, we're going to see that we've got two different type of reactions, at B and at E. At E, oops, here we go. At E, This reaction is only supporting vertical forces. See these little wheels on the bottom? I'm going to zoom in a little bit more. These little wheels on the bottom simply mean that there is no horizontal reaction force at this location. So technically speaking, this structure could slide left to right at E. Think about like roller skates. It could slide left to right. But if I look at point B, I'll see that this is an actual full pin joint. So this prevents motion left and right, and it prevents motion up and down. But again, because it's a pin, it does not prevent rotational motion about that axis. So we're going to see a difference in either pin joints versus what we're going to call roller joints. Okay, so this is a roller, and this is a pin. Again, these are phrases that you're going to study in mechanics of solids in college. If you study engineering and look at anything with structures, you're going to hear these phrases a lot. So I'm trying to use the words that you would use later on, or the terms rather. All right, so here's our steps. Let's go through the process. First, we draw a free body diagram of the entire structure, okay? And that's what we're seeing on the right over here. Now, this free body diagram has the numbers as answers already. We would not be able to do that without actually going through this process. So let's make believe for the moment that we don't know what this number is here and this number is down here. Because again, we know that these forces are applied. It was given in the diagram. I don't think we were given the angles in the diagram. We were not. Okay, so we would have to either measure those angles or figure out what they are as a result of what the dimensions are. And in this case, it looks like these are all 2 meters in length, right? This is 2 meters here, 2 meters here, 2 here. These are all 2 meter members, which is why this truss structure has angles of 60 degrees everywhere, because we're looking at equilateral triangles here. Now, where do these forces come from on the bottom? Those reaction forces are actually used to solve for in the very beginning of the process. So we use the free body diagram to actually determine these two reactions at the bottoms. And I'm going to go through the process of where those numbers come from with our example here. The second step is to isolate each of the nodes and draw pins, nodes, joints, each of those to draw a free body diagram independently for each one. So take a look and let's try to correspondingly show this here. So let's take a look at node A in the diagram. At node A, we've got a 400 Newton force applied downward, and that's shown right here. Okay, so again, node A, there's the 400 newtons. But from node A, we have 3 members. We've got member AB, member AC, and member AD. So these 3 members are all drawn as forces from that node. So this is the force acting on member AB, the force acting on member AC, and the force acting on member AD. This angle of 30 on each side is coming from the fact that we have vertical symmetry here, so we know it's 30 degrees on each piece. So why are we drawing a free body diagram for every single node? Here's the reason. Each of these nodes have to be in equilibrium. They have to. If they're not in equilibrium, then we know that we have a net force. If there's a net force, then there must be acceleration, and therefore our bridge fails, right? The bridge would be moving if there's acceleration. And well, obviously, we all know that bridges do actually move, right? They vibrate, they oscillate, and that's built into the bridge. But what we're saying for a structural nodal analysis is that we assume it just doesn't move at all. So we can say that, you know what, the overall force acting on this object has to be 0. The problem we're going to run into is that when we look at some of these nodes, we don't have enough information to solve for all of those forces. So we have to know some other values for this to make sense. So if I were to start this problem, I would probably start on node B. And let me explain why. Let me zoom in a bit on node A and B. So if I look at node A, the problem right now is that I have 3 unknown forces, FAD, FAC, and FAB. All 3 of those are unknown on node A. And if we think back to force equilibrium, we can do some of the forces in the x and some of the forces in the y direction, which would only give us 2 equations. And if we have 3 unknowns and only 2 equations, we can't come up with an actual solution for node A just yet. So then that's why I'm saying we move on to node B. Node B, we have 2 unknowns, right? And we could think of our sum of the forces in the x and in the y direction to give us the 2 equations. So for node B, that's what we'd be really starting with. Okay. And then finally at the end, like I said, a positive force indicates that it's in tension, and a negative force indicates that it is in compression. Okay, in compression. So like hypothetically, if we look at this, if FAB turned out to be a negative number, it really means that there's a force acting this way on the node, which means that there was a force acting that way on the member. So if hypothetically FAB turned out to be a negative quantity, we would switch the direction of the arrow for FAB. That's what a negative quantity would mean. And then that means that the member that's over here would have a force acting this way to balance it, which is why this member would be in compression if we have, again, a negative quantity for our answer. And the opposite is true for tension. The easy way to remember it, the plus sign looks like a letter T. So that's kind of the way I remember it when I was in school looking at this. Any questions on this analysis piece? I want to go through an example, obviously, but any general questions on stuff that wasn't clear so far? Okay. All right, let's take a look at this next slide. So what we're going to do is we're going to take a quick look at a very simple nodal analysis. We're going to start by determining the reactions at the ends and then the members in each force. Or in each, sorry, the force in each member. The force in each member. So we first start by looking at a free body diagram of the entire bridge. And so far we have most of our things. By the way, anybody ever hear that phrase kip? Kip? Stands for kilopound, like kilonewtons, you know, or kilograms. It's just 1,000 pounds, all it is. So this just means 15,000 pounds. And the other one is 10 kips, or 10,000 pounds. So we've got these two applied loads on this bridge. Now, where could these loads come from? I don't know, really. I mean, the 10 kip load could be maybe like the wind. I don't know what the 15 kip load would actually be, what force would be applied upward, but this is just, again, an example of it. It's not necessarily what you would be seeing when you're crossing a bridge or crossing a structure. What we want to look at is parts A and B and think about what's happening there. So let's go ahead and draw a free body diagram of this. At location A, we have a pin joint, which means we've got a reaction this way, and that's going to be called RAY. And I'm calling it RA for location A and Y for the Y direction. And then at location B, we have the same thing. We've got RBY. But there is a difference between these two reactions. At B, we only have a vertical force, because those wheels, again, at B means it could slide left and right. So there's nothing preventing lateral motion or horizontal motion at B. But at A, we do have a reaction in the X. We're going to call that RAX. Then finally, we have the 15 kip load acting at the top and the 10 kip load acting to the right. So, how many unknowns do we have right now? We've got RAX, we've got RAY, we've got RBY, so 3 unknowns. So if I want to solve for 3 unknowns, I need 3 equations. And from physics, we can think about 3 equations that we're going to use. 2 of them are very obvious. 2 of them are very obvious. We could look at the sum of the forces, right? So we could start, and I'll put my equations over here for this. We could say the sum of the forces in the x direction has to equal 0. Again, because we're in a state of equilibrium for this entire structure. It's not moving. So who can tell me, looking at the diagram, what forces are acting in the x direction? Which ones will we have to list for this? Which forces act in the x direction? Force or forces? Yeah, RAX for sure. And that's an unknown. Very good. And then how about that of the known loads? Yeah, and the 10,000. Now, based on our diagram, they're both acting to the right. So I'm labeling them both as positive forces, okay, because they're both acting to the right in the diagram. So if we look at this, we can see already right off the bat that we can solve for RAX. We can determine the value of RAX just from having this one equation, because it's the only unknown in the x direction. So by default, RAX must equal negative 10,000. And again, what does the negative sign implicate here? And it's not, be careful, sorry, it's not about we're not looking at compression and tension just yet because we're not on the members and the nodes. But for the overall bridge, the fact that RAX, go ahead, Brenda, yeah? Exactly. Very good. It represents that it's equilibrium because we have negative 10,000 and the positive 10,000. So although we drew Rax to the right on our diagram, the fact that Rax turned out to be a negative quantity means that it was really a force acting to the left at that location. And that force acting left is what's balancing this force acting to the right. So that's all the negative sign indicates there on that part. When we get to the members and the nodes, that's when we'll get into like, okay, negative means compression and positive means tension. The second equation we can write when it comes to forces, sum of the forces in the y direction equals 0. But what's the problem here? Take a look at the diagram. Look at all of the actual forces in the y direction. What's the issue with this equation? True, but in the previous one, there was nothing in the leftward direction either. We had both to the right, but I like what you're saying there. You're on the right track. There's something else. Something else. Maybe write out the equation to help yourself see it. What would the equation look like for this in the y direction? Yeah. So, and I'm going to put it all as pluses now because they're all going in the positive direction on our diagram at least. But this is what the equation would look like. What's the issue with that equation? It's pretty obvious, right? What's the issue? Come on. Two unknowns and only one equation. So unfortunately, right now, we can't really finish off this equation until we either know Ray or Rby, right? We have to know one or the other to get the third. So let's talk about how we're going to get a third equation. And this is going to be something not totally new, but new enough. Okay, we're going to use torque now. And what we're going to say is we're going to say that the sum of the moments acting at a certain node, and we'll figure out which one it is, equals 0. Now, if we think back to torque from physics last year, how does an object or a force actually apply torque? What parameter must be involved for torque to actually be applied? For example, opening and closing a door we've talked about. What do you have to have for torque to actually have a value that's not 0? It's not going to be moving in circular motion right now, Joe. So we're not going to have any centripetal forces acting, but good idea there. What creates torque, right? We've talked about this. If I push on a door handle, it's a lot easier than pushing at the hinge, right? What do you need about your geometric setup so that torque actually has a non-zero value? Because sometimes the torque applied is 0, right? What's the formula for torque? Think back on that one. What's the formula for torque? Torque equals what? You got 2 out of 3 there. Yeah, sine, but yes, RF sine theta. That's our formula for torque right there. Not the same thing. So if R is 0, we don't have a torque. And that's what we talked about in class, where when we push at the actual hinge of the door, it's not going to really do anything. It's not going to open because you're not giving it any torque from that. So what I'm getting at is this. We need to choose a node to sum the torques about. And the ideal solution would be to choose a node that has as many forces as possible acting on it, so that those forces don't actually give any sort of torque to the object. So what I'm going to do is, I'm going to either choose location A or location C, because both of those locations have forces acting at them, or at that specific spot. And those forces will not provide any torque if we choose that location. So I'm going to choose location A for today. So I'm going to take the sum of the moments about location A. So we have to think about all of the forces acting on this bridge and how far away they are. How far away is RBY from node A? How far away is RBY from node A? Yeah, 20 feet. So Dennis was seeing, oh, this is RBY, right? This is node A. This gap here is represented by 20 feet in the diagram there. Very good. So we know that the lever arm, or the R value, is 20 feet for that one. Now, if I connect these two, ready? Start at the node itself, slide all the way over, and then look at the force. This is at a nice 90-degree angle here. So this is your angle theta right there. And if we remember, sine of 90 is 1, we don't have to worry about the angle involved in this problem. So when we start looking at the sum of the moments, or torques really, we could start by saying, okay, we've got RBY, and that's multiplied by, actually I should put the length first because we did RF sine theta. So 20 feet times RBY. That's going to be the torque that is generated about location A because of RBY. Now again, it's really sine 90, but I'm not going to put that there. But the second part of these problems you have to ask yourself, and this was back from last year in physics again, is that considered a positive or a negative torque? Does anybody remember the way we associated positive or negative torques? Which was which? How do you know if something's positive torque? How do you know if something's negative? Very good, Joe. Nice work. Yep. So clockwise is negative. Counterclockwise is positive. So here's what I do. I look at this member and I ask myself, if I were to apply a load upward, right, and this was the pivot point, this entire bridge from a load upward would have to rotate this way. So as a result, this force causes a counterclockwise torque. Therefore, it's a positive here. So I don't have to put a negative sign there. Now, the other two forces, these ones are a little more complicated, but the other two forces are acting at location C. Again, at location A, we don't care about those forces because R is equal to 0 for those forces, right? They're literally acting at the node, so the R value for these two would be 0. What's the R value, and be careful here, what's the R value that we could use for the 15,000 pound force? What could we use? How could we treat this? This is something that's not super easy to see, so I might have to redraw it for you. Because we don't have theta, right? We have nothing to do with the angle here. We don't know this angle right there. We don't even know this length right here, right? We're not sure what that length is. We know that this height is 10 feet. That's great, and this is 20, so we could like draw in triangles and do all this work, but that seems like a lot of work. There's something called linear translation of forces. And what that means is this. We can take this 15,000 pound force and we could redraw it anywhere along its line of direction. So I could draw this force acting anywhere here. I could put the force acting here. I could put it acting here. I could put it acting right there at any of those locations. Now, for the sake of our problem, the most ideal location would be to draw it actually acting, and let's use blue for this, would be to draw this force acting right here instead. And the reason I want to draw that force there is because, again, what kind of an angle does it make? It makes a 90-degree angle. If this is the rotating point and we go over to the force and then we look at the force itself, that's a 90-degree angle right there. So I'm going to take this force and I'm going to slide it down until it makes a 90-degree angle. Then I could say, well, what's this distance going to be? If I look at this, right, if I look at this diagram, this is just going to be 10 feet across. I'm halfway across the bridge. So I know that this is going to be 10 feet, and I know that this force is 15,000 pounds, and that's going to cause it to rotate this way, which is counterclockwise. So as a result, we're going to have another positive for the counterclockwise piece. The distance away is going to be 10 feet from the actual rotation point, and it's going to be a force of 15,000 pounds. And we're almost there. We have one more force to take care of right now. So again, we redrew this force down here as 15,000. What can we do with the 10,000 pound force, do you think? What can we do with the 10,000 pound force to make that one easier like we did with the 15,000? Think about using that concept of linear translation. We can slide a force any direction along its, anywhere along its directional, is vector's direction. So I could slide the 10,000 pound force right or left because it's a horizontal force. Which way do you recommend I slide it? Try to look at the original diagram of the bridge, look at the way we slid the 15,000 pound force, and try to use that as context clues to figure out which way you would move the 10,000 pound force. I think you're right, Joe. How come? What are your thoughts? If I slide it, I'll do it. Let me do it, and then you tell us, okay? So I'm going to slide it to the left. I'm going to put it, oops. I'm going to put it acting pretty much along this spot right there, Joe. Okay, so I'm going to move it over to where it is, and this is my new 10,000 pound force. I'm going to get rid of this one. So why would I do that, Joe? What does that allow me to have now as a measurement? Look, yeah, that's right. Look at the original diagram, right? Look back up here. We're given something else that we haven't used yet that we probably could write on our diagram. Not that one, no. For example, let me make it a little more clear. When this 10,000 pound force was located here, we didn't know how far away this was, right? We didn't know what this length was here, and we didn't know what the angle was either. So that was tough. But now that the force is over here, what do we then know? Good. We know that the lever arm, or the length or the distance from the actual rotating axis, is 10 feet. This is a 10-foot gap from top to bottom. So that means that this is also 10 feet. Now, we didn't know this angle earlier, right? We had no idea what that full angle was right there. But now, take a look. Again, we have a 90-degree angle. So in this process, what we're going to notice is that we want to slide our forces around so that we get a lot of 90-degree angles. So this last part, the key though to this one is to recognize that this would cause a clockwise torque. And think about it here. Put your pen here, right? Again, here's the rotating axis. Apply a force this way. The whole bridge is going to rotate in that direction. If this is your hinge right there, it's all going to rotate that way. So this is a clockwise torque, so that's a negative torque. And again, it's at a height of 10 feet away. And it's a force of 20,000 pounds. Oops, I should put pounds. And last but not least, the entire torque sum has to equal 0. The reason it equals 0 again is because it is preventing rotation. The bridge does not want to rotate. So we use torques, right? 3 different torques there, and we specifically chose node A to work on because it had a lot of forces acting there. What does this allow me to do? Well, look at this equation here. I've only got one unknown in this whole equation. If I had 2, if I had RBY and RAY, well then I could use a system of equations, right? I would have 2 equations and 2 unknowns. I could do that also if I had 2 unknowns here and then 2 more unknowns here. But RAY, which is unknown in this equation, does not appear in this equation anywhere. RAY does not appear in this equation simply because we chose location A to be our sum of the moments about. We specifically chose this to be the rotating point. So RAY, which had a value here, is at a R value or distance from the pivot point of 0. So it never had any torque applied from it, which is why it's not appearing in this equation. Now, with that said, what we want to do is we want to solve this for RBY. So we would rearrange this equation here. I think I have the number written down to save us a little bit of time. Do I? No, I don't have it written down. Awesome. I thought I had it written down here. Let's see. What would this become? Negative 200,000. We got 10 times 20,000. That's going to be a negative. I'm going to add that over. From that, I'm going to subtract 150,000, which is 50,000. Divide that by 20. We get 2,500. And the answer I get is positive in this problem. And again, what does that mean? about the fact that it's positive. It simply means that RBY, which was drawn in the upward direction, is actually in the upward direction. When we got a negative earlier, we were told, well, RAX, which was drawn to the right, is actually a force to the left because it was negative. And once we have RBY, we can take that value, plug it back in up here, right? Take this value here, plug it back in, and then solve for RAY. And that'll just be what? Let's see, move the 2,500 over, move the 15,000 over. That's going to be negative 17,500. Which tells us about RAY. It tells us that RAY, although drawn, although drawn upward in the diagram, RAY is actually a downward force. A downward force. And let's ask ourselves why that makes sense. Can somebody explain the logic behind that? Why RAY turned out to be a downward force in this problem? So this could move right, left. It could, we say, yep. How about this one, Brendan? This 15,000. This tells us what? Just generally, the bridge is being pulled which way, according to this? Yeah, upwards, which is interesting, right? So if it's being pulled upwards, we need to have some downward force. This is the downward force that's combating not only this pulling upward, but also RBY, which is also pushing upward. Okay, RBY is pushing upward because, again, this 10,000 pound force here would cause this whole thing to rotate this way, right? So this has to respond by pushing back up. So these two are pushing up, and as a result, RAY turned out to be negative, pulling down. So this is all we've done so far, by the way, for this is the reaction forces. That's what we just did with this analysis. We have not even got into nodal analysis at each node. But timing-wise and stuff, I'm gonna pause us there because this did take us a while. We're almost even through the whole period. But what I want to point out is that it's a lengthy process, these problems. You have to first find out your 3 reaction forces, 1, 2, 3, and then once you know your reaction forces, and we'll do this next class, we can take a look individually at node A, at node C, at node B, and do a nodal analysis to find the force in each of these 3 members, in each of these red members here. All right, that took us a little longer than I had hoped. So what I'm going to do is I'm going to let you guys go for today at this point, timing-wise. If you want to, I say you feel free to explore the app that Jack had mentioned. I forget what it was called. I have to tell you guys because I have it here.